Hello and welcome. So, we are still thinking about the future of nanobiophotoниcs, and today let us discuss bio-inspired materials. Bio-inspired materials in the sense that the material can be artificial, it can also be natural, but it can be artificial mostly, inspired by the hierarchy, the organization, the complexity and the variety that is available in naturally existing material. So, let us get into it. So, as I was talking about butterfly wings in previous lectures, bio-inspired materials in photonics refer to materials designed or inspired by biological system that exhibit properties related to light interaction, emission and manipulation. Biological systems have evolved tremendously. The complexity is simply mind blowing. The complexity of this moth's wing, as you can see, the different color, the different organization, the different structure, none of them are because of some chemical dye has been used. It's simply the nanostructure is such that it is reflecting a particular light and rest of the lights are all destructively interfered, killed off. Closely under the microscope, they will probably look black and white or grayish or something like that, but when you look from a distance, several bombardment of light produces a particular color. Look into them with one particular wavelength of light, which basically you can do it in a microscope, specialized microscope nonetheless, and you will be able to see the inherent nanostructures. So, moths have a structure of ordered cylinders in their eyes that do not produce color, but instead reduce reflectivity. This concept have led to anti-reflective coating as well. So, this is another such example. Many of you have seen or use it or probably have it is available. The wings of peacocks, national bird peacock, and it has this wonderful color. And it is not because of the presence of any dye, it is because the structure, the nanostructure here is different than the nanostructure here, and this is different from this. Each nanostructures allows only a particular wavelength of light to survive. Thereby, this is blue, this is whatever color you call it, yellowish something, grayish, yellowish. This is, well, I am partially color blind, so this looks green to me. So, you decide what it is, different shades of blue, green, whatever. So, the organization of these nanostructures are not random. They are in a particular pattern, so that the a particular overall pattern, particular design and overall design exist inside the wings of a peacock, and we can utilize this organization, this complexity for various applications. Light harvesting antennas, materials mimic the way natural photosynthesis system capture and transfer light energy. Photosynthesis is basically capturing the light and converting, utilizing that light to create oxygen at the end. It is a photochemical reaction, right? Photosynthesis. Can we artificially do it? Getting inspired by photosynthesis, that small lamellas, the plant cell, the leaf cells do, can we artificially make a photosynthesis in a chip? We have photonic crystals, obviously we discussed this, chromophore embedded polymers integrating light absorbing molecules into polymers to create flexible photonic devices, photonic nanomaterials, nanoparticles with properties like plasmon resonance inspired by biological structure can manipulate light at nanoscale dimension, bioluminescence properties, molecules like GFP, and nanomaterials for enhanced sensing, nanostructures inspired by these sensory capabilities. So, for example, this nanostructure is specifically suitable for reflecting blue light. We mimic that, create an artificial material that will only work at blue light, and then try to utilize it as some sort of a sensor, and try to look into the different wavelengths of reflected by some other material, utilizing it as a sensor. The advantage, as I keep on saying, are plethora, number one being biodegradable, eco-friendly, but having said all of that, they are highly efficient. The most important thing is efficient. I keep on saying, think how efficient your body is, how much amount of signal your brain is processing per second, how much amount of input at a time your brain is capable of handling. Plethora of sense organs, it's talking about light, it's processing light, it's processing sound simultaneously. At the same time, there is touch, there is smell, and then it is all processed and finally converted into some sort of a memory or some sort of attention, some sort of concentration, so that the entire concept goes in. So, if this is not efficient, what is efficiency? How many computers do you think can be this efficient processing wise, simply from a processing standpoint? Different types of data all processed together. Computers can only process one type of data in the form of 0 and 1. Yeah, it cannot process different types of data. Give anything to computer processor, it will convert it into 0 and 1, and that's what you are getting. Anyways, tunability, these materials can be engineered to respond to specific wavelengths. Sustainability, learning from nature's design can lead to sustainable energy efficient photonic solutions. Self-healing properties, another thing, some organisms can repair themselves, bio-inspired materials can incorporate self-healing mechanism, and of course, biocompatible. Bio-inspired materials often share similarities with biological systems, making them inherently more compatible with living organism. Applications, as I was saying, you can make large number of sensors. Bio-inspired photonic materials make highly sensitive and efficient sensors. You can have displays, photonic crystals, and that thing that you just saw, the wing of a peacock. Can we make nanostructures and make a display with variable tunable colors without having any chemical involved? Light emitting devices, LEDs, bio-inspired materials can enhance the efficiency of light emitting diodes. Optical communication, enhanced light manipulation properties can be applied for optical communication. I read a paper about from I think Harvard, Marco Loncher's group, where they were discussing about on-chip communication, photonic crystal, photonic wire based on-chip communication, and there was some sort of inspiration from biological materials. Solar cells, learning from natural light harvesting systems can be improve the efficiency of solar energy conversion. A large plethora of solar energy is not absorbed, only a small plethora is absorbed, that is converted into electron hole pair in solar cells. But using these kinds of different nanostructures, not only you can increase the absorption, but also make a variety of wavelength, variety of light, all the 7 colors, infrared, ultraviolet being absorbed and thereby converted to electron and hole pair. Light harvesting dendrimers. So, dendrimers are these branch like molecules which has a core type structures, and then they branch out. They have a core type structure and then they branch out, and this branch then opens into several branches. So, it's like this. So, researchers are talking about these kinds of branched small molecules for making artificial photosynthesis. In natural photosynthesis, arrays of chlorophyll molecules do these various biochemical reaction, photobiological reaction. The idea here is to make utilize of these molecules in chip and thereby create artificial photosynthesis. Artificial photosynthesis, where presence of light will give oxygen. Yeah. So, light energy is converted to oxygen. So, several different things are going up, and the work is still under process. Maybe in 5 to 10 years, you will see remarkable development in some of these areas, some, not all. Some areas will get lost, and several new areas that I have not covered might come up. This is simply looking into the future and trying to make a forecast. So, in conclusion, bio-inspired materials draw wisdom from nature's design principles. By replicating nature's optimization, these materials often exhibit far improved properties than what we can think of and create. Bio-inspired materials transcend boundaries, finding utility in photonics, medicine, architecture and beyond. There is a building, it is not part of nanobiophotoниcs, there is a building in I think Spain or somewhere where they try to mimic ant hill, ant mole. Ants come together and prepare some sort of a colony, usually underground or nearby some place where they live, and that remains cool. So, people took inspiration from that and created a structure, created a building which has ant hill, ant mole hill like structure, and they found out that it is naturally cooling. Even at hot sun, the interior of the building is naturally cooling. So, architecture have already utilized some of the design present in beehives or ant mole hills, etc., ant moles. Photonics, why should photonics remain behind? Dendrimer stands as remarkable example of precision in polymer design, boasting intricate branching structures through controlled synthesis. So, these are the concepts that I covered today, and these are my references. Please go for Current Opinion in Chemical Biology. This is a fascinating paper that I read. Light harvesting dendrimers by Balzani is also quite nice. Thank you very much.